Hi everyone. So for my wiki, I was given an NMR spectrum. So I'm going to tell you how I went about doing it. So I'm going to refer back to my computer screen and my paper simultaneously throughout the video. So the first thing I did was calculate the degree of unsaturation for the molecule, and in doing so, I saw that there was 10 carbons, there was 12 hydrogens, there are no halogens, and we need to add a constant of 1. So 10 minus 12 over 2 plus 1 is equal to 5. Okay, knowing that we could potentially have a ring and several bonds. So several double bonds, I'm sorry. The first thing that I do when I do an NMR is look for any outstanding ppm values that correlate to a specific functional group. So the first thing I did was I saw that there was a 9.88, and I noticed that that value correlates to an aldehyde. So I'm trying to think, okay, there's an aldehyde in this molecule somewhere. So I already have that. I've already written down the structure of that, and in doing so, the first thing I did was I just drew this. I didn't draw the ring yet, but we'll get to that point. I drew this, and then I continued. I also know that 0.9 ppm is correlated to a primary carbon, and it shows that the primary carbon it's a triplet, so meaning two neighbors. So I can try to look for a primary carbon, a CH3 that is close to two other hydrogens, so probably a CH2. And what I do is I try to do like a mapping system. So I'm saying, okay, CH3, that's the 0.9 value, the primary carbon that we were given, with the two neighbors. And so I try to like map it out. I'm like, okay, so it's going to be near a CH2. And I just continue to do that for all of the values. And in doing so, I encountered this molecule. So it's a gradual process. It's not going to come in like instantly when you look at the NMR spectrum. It's just something you have to get used to and doing. So yeah, this is the solution for C10H12O2. Continuing for question number 2, it says a nitrogen containing compound exhibits no absorption above 3,000 centimeters, and but does exhibit a band of medium intensity at 2250 centimeters. What functionality does the compound possess? So this is just a simple case of understanding your IR values. So what I said was, since there's no absorption above the 3,000 point, and there's a medium intensity at 2250, and it contains nitrogen. And if we look at our IR values, the only compounds that have nitrogen are the amines and the nitriles, and they exist at nitrile exists at 2210, 2260, and the amines exists at 1030, 1230, and 3300 and 3500, but I already stated that it doesn't go above 3000, so we can just assume that it's a nitrile, and that's just a simple solution for that one. Continuing on, we are given a series of molecules that have differing degrees of carbons. So the first thing that we need to know for a carbocation, that the most stable carbocation is usually correlated to a tertiary carbon, and going down is lesser in stability. So a secondary carbon would be less stable than a tertiary carbon, and a primary carbon will be even less stable than a secondary one, and lesser than a tertiary. So continuing that thought process, we are given a series of carbocations. So the first one is going to be in retrospect to all of the collective, it's going to be the second most stable. This one is a tertiary carbon, so it's going to be the most stable. This one is a primary carbon, so this one is This was going to be the third stable. And then this one I had like, when I initially did, I had did not perceive this correctly. I thought those were methyl groups, the H's, but in reality, there are no substituents on this carbon. So this carbon is the least stable. Now, the logic for carbocations, stability is the inverse for an anion. So the primary carbon and carbon that has no substituents is going to be the most stable. So this one is going to be the second one because it's the primary carbon. This one is going to be the fourth one. This one's going to be the third one, and this one's going to be the first one. Now, radicals have the same logic as carbocations because they're highly reactive, and they're going to want to make, they're going to want to connect. So they have to have an environment that is similar to a carbocation. Hence, a tertiary carbon is going to be the most stable bond to exist for that reaction. So it's just essentially the same order as the top line. 2, it's going to be the second, the first, the third, and the fourth. Now, continuing on to my final and last question. Which of the following best represents the carbochlorine bond of methyl chloride? So this is just a simple dipole kind of question. We're just looking at the, we're going to be comparing electronegativities of these molecules, of these atoms specifically. And so the first one we're given is a positive dipole and a negative dipole on the chlorine, which should give you an indicator that this might be the correct answer because it is a, sorry, my cat is like going off right now. It should be a clear indicator that the electronegative atom is going to want to pull those electrons towards itself, hence why it's going to have a negative value for its dipole. And all of these other values don't really make sense. The carbon's not going to be the one pulling the electrons. They're not going to be the same in terms of positive charges, and they're not going to be both negative. And this one just is, an improper, there's not even a carbon-chlorine bond here. So, yeah, I think I don't know what that's about. But the first one is going to be our answer. For the questions that I have derived by myself, I will be uploading this as a PDF so that you can look through this. But I'm just going to read through my questions. It says, what best represents the bromide carbon bond of methyl bromide? So that's like similar to the last question that I just wrote, which is the Markov product. So this is knowing the secondary, tertiary rule that I just was explaining. So you have to look at that and differentiate, knowing the ppm values and what they correlate to what specific functional groups and how that relates back to IR. These are questions that are connected to each other. So I wanted to test that knowledge. And where's my file? Okay. And piggybacking off of the third question that I showed, I wanted to show what is the most, I don't know why I said highest stability. Rank the stability of the alkenes based off the groups that I've shown, one being the highest. So this is just basically knowing the relationship between energy and isomers, whether it's a trans or a cis molecule, so you have to know. And yeah, I hope my explanation was coherent and you were able to follow along and have a greater understanding of the material.